So very good afternoon everybody. This is Dr. Vaibhav Pandit and today we are going to discuss the topic from our subject that it is image processing. And now the topic here we have the basic spatial filtering here. So up till now we have gone through few of our live sessions related to this particular subject, whereupon we focused how exactly the digital image is first of all formed and how we represent that particular image. Afterwards, few of the basic processings onto the images were taken, and in the previous session we have discussed about histogram processing, the most popular histogram equalization and further histogram matching we have addressed. So now today's our topic is basic spatial filtering here. So right from last two sessions we are into the domain of spatial domain operations to be there for image processing purpose here. So still we continue here into the same domain, spatial domain, and next we can switch to the frequency domain here. So now under the title basic spatial filtering, first of all we shall see the mechanics of spatial filtering and a brief introduction to what exactly the spatial filtering mean to us. So when we talk about the term spatial filtering, so that time we encounter with such operations. Those operations are with respect to the values of the image pixels into the neighborhood for the pixel under consideration here, and because of this particular such concerned portion into the image domain here or image panel here, we call it a sub image. So here we have a sub image and that holds the same dimensions as we talk about the neighborhood. So the neighborhood can be of 3 by 3 dimensions, 5 by 5 dimensions, 7 by 7 dimensions. This way we can go on. If we take 1 by 1, so it will be the pixel under consideration itself. It won't cover the neighborhoods here. So the neighborhoods are the neighboring pixels having different kinds of the brightness levels, what we call the intensity levels here. So few of the neighbors will be on left hand side, then right hand side, upwards, downwards. So this is all possible, adjacent as well as the diagonal neighboring pixels here into the image plane here. So this particular sub image, as we focus on to the neighborhoods of a certain pixel, is very important, which can be used for the spatial filtering here. It has a main role. So this sub image is most of the times also called up by the names. It can be called as a filter, it can be called as a mask, it can be called as a kernel, it can be called as a template, or it can be called as a window. So it is a sub image. So sub image will also be having certain dimensions. If we denote the entire image, the dimensions by capital M by capital N here. So by small m by small n, a portion of the entire image we can represent by this sub image, and we can treat it to be the name filter or mask. So mostly we go for using the mask here or simply the template here. Now in this particular case, the values into such sub image are not referred directly to be the pixels. They are basically the pixels but as the coefficients, because with the help of these coefficients we are going to make the changes into the intensity levels at the original level, so that the more effective output image can be made possible here. So these are basically operating over, that is why these pixel intensities are called as the coefficients here. So this is the very important point here. Now when we talk about the term simply filtering, not going for first of all the spatial case here. So filtering is having a little background with the use of the Fourier transform, a very popular mathematical tool here. So this Fourier transformation takes us to the frequency domain here. Few of the application tasks are quite convenient to work into the frequency domain. In less number of steps we get the same output here. So this is with respect to the background from signal processing here. But when we are talking about the entire spatial filtering, so that time this particular spatial filtering is having the image processing operations performed directly onto the pixel values or simply the pixels, and thus referred to as the spatial filtering here. Now directly coming to the illustration that shows us how the mechanism of spatial filtering work upon. So for that purpose, let us have a visualization of the diagram here. So the mechanics of spatial filtering better explained with the help of this diagram. Now you focus on to the top portion here. Here we have first of all the horizontal orientation dimension represented by the y-axis, and here it is the x-axis, another dimension here. So with these dimensions, the image region under consideration, here it is I have marked upon, and it can be hereafter represented by image f as a function of x comma y. So already into the previous sessions I have got it clear that f represents the intensity level, whereas x and y, these two parameters provide us the exact location of the pixel into the image plane here. So there are several pixels here. So when we go by row wise and along with column wise, we have different pixels. So for let us say this pixel, we have the row number 3 here, and we have the column number 2 here. So x will be holding the value 3, y will be holding the value 2 here, and let us say this is quite a brighter pixel here. So into the 8-bit environment, when we are representing, we have total 0 to 255, that means total 256 shades at the grayscale here. So let us say it is representing 200 intensity, that is the value of f. X will be equal to 3 here, y will be equal to 2. So this is what the image plane here we have, and when we want to perform the spatial filtering, so that time what we have talked about, a filter or a mask or a template or a window, here it is represented. So this mask, here we have the dimensions of this mask to be of 3 by 3 here. So you can see here into the rows we have 3 rows, into the columns we have 3 columns, a square size we have. So the pixel under consideration to be at the central level here, and with respect to the central pixel, the neighboring pixel intensities are taken into the consideration. Hence this particularly forms a neighborhood centered at the pixel under consideration, and this mask is to be operated onto the entire image plane. So when we zoom this much of portion, the magnified view can be taken out like this. So in the magnified view, you can see the pixel under consideration when it is represented by f in the bracket x comma y. Their neighborhoods are f in the bracket x comma y plus 1 on the right hand side. On the left hand side we have f in the bracket x comma y minus 1. In the upwards we have f in the bracket x minus 1 comma y. In the downwards we have f in the bracket x plus 1 comma y. So this way these are the adjacent neighbors. The diagonal neighbors are f as a function of x minus 1 y minus 1, f as a function of x minus 1 y plus 1, f as a function of x plus 1 y minus 1, and f as a function of x plus 1 y plus 1 here. So total here we have 8 neighbors, and along with the own pixel intensity at that location we have a neighborhood of 3 by 3. Okay. So now this is what the image pixels, those are under operation by the mask, and the mask panel I can say here it is. So this mask can be designed as per the requirement here. So whatever the things we put up to form this particular mask are called as coefficients. Just now we have talked about. So for the pixel under consideration, let us denote the coefficient as w in the bracket 0 comma 0. The adjacent coefficients are w in the bracket 0 comma minus 1, w in the bracket 0 comma plus 1, w in the bracket minus 1 0, w in the bracket we have 1 comma 0, then w in the bracket minus 1 minus 1, here we have minus 1 plus 1 minus 1, then 1 plus 1 here. So this way these 9 coefficients, those are arranged into the 3 rows and 3 columns. like this are supposed to operate onto the image pixels from the original or the input image, which are also 9 in number. So this is what is called as spatial filtering, and this mask we have to move onto the entire image plane starting from the image origin as it is shown at the top left corner here. So now more details we can see here. So this is the process that consists of the filter mask to be moved as we have talked. So this is to be from point to point location here. So any point we can specify with the help of the locations provided in terms of x comma y here. So by operating with the help of the filter mask, it is supposed to generate response to that particular filter or response to that of template here, and this response is generated by using a predefined relationship. So while designing this particular spatial filter, we have to develop the logic that what way it is supposed to generate the intensity level of the output pixel for the output image here. Now we have different kinds of logic to be developed for, and depending on we can have simple classification of the spatial filtering also. The very basic classification can be the linear spatial filtering and that of the non-linear spatial filtering. And when we are talking about the linear spatial filtering, the response is given by the sum of products, what we abbreviate as SOP here. You just focus your attention to this particular point. The first type of the spatial filtering is the linear here, and here we are going to perform sum of products here. So first of all, product of what two elements here. So the product is nothing but the multiplication. The multiplication is to be carried out between the filter coefficients, filter elements, and the corresponding pixel intensities here. So as we have a neighborhood, for example, of 3 by 3 dimension here, so for the 9 combinations, we can have the 9 multiplications of the filter coefficients represented by W, and the pixel intensity is represented by F here. And all these multiplications are to be summed up, which is going to give you the output pixel intensity. So this simple process can be called as a linear type of the spatial filtering here. Now we move on. Mathematical representation for this, as we have taken the example for 3 by 3 mask here, when the resultant pixel intensity is to be denoted by capital R, what we call as a response also, the mathematical expression to have it represented is like this here. So capital R is the output pixel intensity, as I have talked about the multiplications or the product here. This is the first combination. W in the bracket -1 comma -1 is to be multiplied to F in the bracket x minus 1 y minus 1. So as we are going to have it stacked overlap onto the image plane here, so this particular filter coefficient is to coincide with this particular image pixel here. They are to be multiplied. All such 9 multiplications are to be collected and finally added with each other. They have to be summed up. So this is what the mathematical representation and what we call it to be the linear spatial filtering. Adding certain more information here. So the sum of products for the mask coefficient with the corresponding pixels directly under the mask is the very important note here. Along with, when we are talking about the coefficient that is at the center, represented W in the bracket 0 comma 0, this is going to coincide for the pixel under consideration. Out of the 9 pixels, the central pixel is the intended one here, and rest of 8 others are the neighbors of the concerned pixels here. So this is what the note here. So when we have the central coefficient coincided with that of the pixel under consideration, all the other filter coefficients are definitely going to match with the other neighborhood pixels for the concerned image pixel here. Now after this important note, the general linear filtering of the image, we have represented the response capital R here. So when we have the entire pixel of the dimensions, image of the dimensions capital M by N, and the filter mask is of the size small m by n here. You just focus your attention here. This is the entire pixel dimension and the filter mask is of the small size. So for a local portion here. So this is by small m by n. So then this particular filtering can be represented by g as a function of x comma y, which is the new pixel intensity that is to be achieved by this linear type of spatial filtering. The process is here. Here we have the multiplication of the filter coefficient with that of the pixel intensities and finally the summation. So in this mathematical represent small a and small b. So they are nothing but small m minus 1 divided by 2, small n minus 1 divided by 2 here, and this is supposed to be operated onto the entire image plane. Hence, we have to range for x and y right from 0 to capital M minus 1 and capital N minus 1 here. So, this is what the simple process of linear filtering as we have already shown into the mathematical equation here. Now, this is quite similar to the convolution process that we have already seen in our subject, and this is mostly the frequency domain concept here, and because of this particular reason the linear type of the spatial filtering is also known by the convolution of a mask with an image, or we can simply assign the task as like convolve the mask with the input image here and get the output of spatial filtering. So this is nothing but the linear spatial filtering here. So in the similar fashion, the filters or the mask or the templates or the windows that are now used for the spatial filtering are also identified by the terms convolution mask or the convolution kernel as well. Now after this linear type of the spatial filtering, we have another type, that it is expected non-linear spatial filter. Here there is no linearity here. So non-linear spatial filters are also supposed to consider the neighborhoods of the pixel under consideration, and also the mask is to be slided from one portion from one pixel to the another pixel here. Now what is the difference between the linearity and non-linearity? From the title we can judge, but the filtering operation is here based conditionally onto the values of the pixel into the neighborhood, and here the explicit use of the coefficients is not there in the sum of products manner here. So SOP is very simple. Just find out the multiplication of the coefficient and the pixel intensity and find the summation of it. So it will result into the output pixel intensity as a result of this linear here. So this is not the case in the terms of non-linear spatial filtering here. So for example, if you talk about the noise reduction task here, so this can be better obtained with the help of this non-linearity here. So here we have a basic functionality to compute the median gray level value in the neighborhood in which the filter is to be located here. And here the computation of the median is non-linear operation, as of course we know here. So for these two basic categories of linear type and non-linear type here, we have the smoothing and the sharpening operations. Definitely we are going to see into the details. Now the very important task for spatial filtering, I hope you have got it cleared, that you should have the original image plane, and into the image plane whatever the pixel initially you have under consideration, you have to take into the account its neighborhood pixel intensities, taking the concerned pixel at the center here. So we shall be having a design of a mask to operate onto all these pixels while sliding from the origin towards the right hand side here and downwards as well here. So here if we are having this particular mask at certain borders or the corners here, there are several issues, those have to be solved here. Hence the simple question comes to everyone's mind, that what happens when a center of the filter approaches the border of the image here. So for example, we consider a square mask of general dimension, we represent n by n here. So at least one edge of such a mask will have to coincide with the border here. So that time the criteria for operating this particular mask is to have a distance of n minus 1 by 2 pixels maintained from the border here. So if this is the case here, so we shall be having the output pixels inside the border here. So we shall be having the limited size here. The simplest way to handle this situation is to limit the excursions of the center of the mask here. Now moving further, the resulting filtered image, as I have talked, is now smaller into the dimension. So you can say that there it is a loss of information, and we are not intended to have losses of information while we process by the various image processing operations here. So if we expect the filtered image, the spatially filtered image of the same size here, so that time we have to filter all the pixels only with the section of the mask that is fully contained in the image. We don't have to go outside the border of the image. So with this approach, there will be the bands of the pixels near the border that will have been processed with a particular filter mask here. And other approaches we can go for using the padding here, padding the image with the additional elements. Those are in the rows and columns, and the value is of 0. This is also known by 0 padding here. So this padding is stripped off at the end of the process here, and so that we get to the intended results here. So this gives size of the filtered image to the expected size that it was in the original case here. And the only way to obtain for the perfect here is to maintain the criteria as we have talked about, n minus 1 divided by 2 pixels for the image that has been already padded by the 0 elements here. So up to this much of point, the concept I hope is very clear, and based on this linearity and non-linearity, while making the mask operated onto the entire image plane, we have the several types of the spatial filters here. So most popularly we have first of all the smoothing spatial filters here. Now when you just see at the title here, the smoothing term indicates what the visualization of the output image should be there as compared to the input image. See, when you are doing image processing operations, you will be provided or you will be having your own data set of input images for betterment. What is required, whether to smooth the region or to sharp the region, or whether to carry out something else locally or globally, depending on that we select the different image processing operations here. So here the spatial filters, those produce the smooth results that we are to talk about. So here the smoothing spatial filters are generally using for the blurring purpose, the blurred images or the reduction of the noise into the original image here. So the blurring can be better defined in this way, as well the noise reduction can also be detailed. Now the first type of the smoothing spatial filters is the smoothing linear filters here. Here the output of smoothing by the linear spatial filter is simply the average of the pixels contained into the neighborhood of the filter mask. So this is the very simplest and basic operation which have a linearity property to produce the output result here, and it is of course the popular because in minimum duration you can achieve the averaging and get the result smooth for the intended or the entire portion here. So because of the averaging here, the smoothing linear filters are also known by averaging filters, and they are sometimes also referred by the name low pass filters here. So the process of this particular smoothing linear filters is there. We can go as like the results into the image with a reduced sharp transition as we are going to achieve the smoothing here. Then the noise reduction, the application we have talked about. When we talk about the edge of the pixel to be inside, well inside or at the middle of the image plane here, they are also to be characterized by the sharp transitions of the gray levels here. So as like for the 8-bit environment representation for the image. Here we have 256 gray levels here. When you select one of the value under 10 and another value after 100 here, so there it is a sudden change here. So we have the sharp transitions of the gray levels. The effect is of course of smoothing. So when we have a sharp transition, so that time it needs of course the smoothing here. So here we have the averaging filters, the undesirable side effect that they blur the edges here. So to avoid this particular effect, we have to also consider taking other types of the filtering as well here. And this is all about the spatial filtering here. Now what exactly the type of mask that we are going to use for the smoothing spatial filters, it is well represented with the help of this particular diagram here. Here you can represent the 3 by 3 order, the smoothing or the filter mask here. So in both of the filters we have two masks or the two filters you can see here. So for averaging purpose, whatever the filter coefficients we have, the summation all of these ones comes to be 9. Hence for averaging we divide it by 9 here, whatever the summation comes up here, and this particular summation comes up to be 16. That is why we multiply 1 by 16 to this particular averaging filter mask here. So the information, I hope it is very self-explanatory for this particular spatial filtering of the smoothing type here. We have the two masks described, that is for 1 by 9 into the filter mask and then 1 by 16 into the another filter mask here. The mathematical representation of this smoothing filtering can be better represented with the help of this expression here, where we have g as a function of x comma y, the output or the average pixel intensity by this smoothing filter mask. Here we have the filtering coefficients operated onto the pixel intensities they coincide with, and we divide them with the summation of the filter coefficients. So this is what the averaging is here. Now we have one example that better gives you understanding what are the visual effects as we go for operating with this type of the filtering here. So we have the sections right from A to F here. Now you can see here the original image of 500 and 500 pixels. This has been taken from the textbook here. So various elements you can see here, and as we operate it with the variation into the mask size here, we have different effects as we can see from this image to this image. You can see at the last image the blurred effect can be clearly seen here. So of course these particular filters are very popular because of the short time they have taken, and afterwards we are also getting the blurred effect. So with the use of another filters as well, we can get rid of this particular blurring unwanted effect here. So here we have one example where we have the original image represented onto the left hand side here. Here it is the image from the Hubble Space Telescope here, and when it is processed by the averaging mask of the dimensions 15 by 15, you can see a blurred image here. So get the things extracted from this particular image when we perform thresholding along with this particular spatial filtering, we get the resultant image as like this, that is represented onto the right hand side that I was talking about. Now the second type here is the order statistic filters here. So here this is of the non-linear type here, as we have talked about. I hope the thing is very clear here. Here the most popular case is of the median filter here. Out of the pixel intensities, those are covered by the filter mask having certain neighborhood size here. We have to determine the median of the value from the set here, and that we have to assign to the output here. So this is also the very effective type of the filtering here. So it is not having the linear relationship but a non-linear here. This is also popular here. We have another example here. You can see The input image is the X-ray image of the circuit board, that is having salt and pepper noise here, that is represented onto the left hand side. We want to get the noise reduction here. So when we perform by 3 by 3 averaging mask, you can see not much effect of noise reduction you can obtain after this averaging here. So when instead of 3 by 3 averaging mask, when we opt for the 3 by 3 median mask, so that time we get a quite clear image onto the right hand side. So this is what the selection of the filters should be application oriented. When you have the application of noise reduction of this particular type, especially the salt and pepper noise, you should opt for the median filter instead of the averaging filter. And when you have certain application where smoothing is necessary, so that time you can go for opting the averaging mask here. Now based on to this salt and pepper noise reduction, we are also supposed to take one problem that can come into your examination for the subject image processing here. Now after smoothing spatial filters, we have the another popular type, that it is sharpening spatial filters. The effect is quite different here. So here the objective is of making the output image more sharper, that is to highlight the very fine details those are hidden into the image plane here. So this is nothing but to enhance the details those are blurred here. So this is what the sharpening we are supposed to carry out here. The application areas ranges from the medical imaging to the industrial inspection, the autonomous guidance into the military system here. So the image blurring could be accomplished into the spatial domain by pixel averaging, and when we have the spatial differentiation, we can achieve the sharpening here. Mathematically, this differentiation we can definitely show you for the input intensity label, pixel intensity here, expression for this sharpening filters as well here. So when we have the spatial differentiation, we have the derivative operator here, and this is proportional to the degree of discontinuity that we see for the intensity labels into the image plane here. So this image degradation, when we use for the spatial filtering here, it enhances the edges, the other discontinuities as like the noise, and we get the sharp image here. This point is very important. It has the behavior very opposite to the earlier behavior of the spatial filter here. Now a basic definition of the first order derivative of the f of x can be shown here. So del x of f can be equal to f of x plus 1 minus f of x here. So if we go for one more order, that is the second order representation can be made with the help of this particular mathematical expression here. Now here, when we consider the two variables f of x comma y here, we have the example represented in the visual form here. So the effect you can see. Now here we have part a simple image here. In the part B, we have a one-dimensional horizontal gray level profile along the center of the image and including the isolated noise point here. And when we have the profile simplified here, so the points are joined by the dashed lines to simplify the interpretation here. So at the bottom into the part C, you can see the first derivatives computed and the second derivatives computed corresponding to the pixel intensities into the image strip here we can say here, and those are arranged into this graphical plot like this on the vertical axis as well. Now the more description for this particular example can also be simplified, understood with these particular points here. So this is of course for the sharpening purpose here. And now as we have talked about the orders of the differentiation here, the most popular thing in the sharpening filters is the use of Laplacian. So the Laplacian is of the second order partial derivation here, and of course it is for the image enhancement here. The Laplacian over the image sample can be denoted by this particular mathematical expression here. Here the del square is the second order derivative operator called as the Laplacian here, and the input pixel intensity will be modified with respect to these two parameters. Here the example can be visualized here. We have again three parts. So we have part A to be the filter mask to be used for the implementation of a digital Laplacian here. Into the part B, we have the mask used to implement the extension that includes the diagonal neighbors, and then at last part C, and then the part D here, the other implementations of the Laplacian here. You can simply take them to be the kernels. So these are the various mask options those we can prefer for sharpening of the image here. The visual effect can be better understood with the help of the example here. We have the input image of the north pole of the moon here. When we operate it with the Laplacian, we obtain the output that we can see on the right hand side here. And when individual Laplacian is to be there, the scaled form can be represented into the part C in the second row, and the enhanced image after sharpening you can see into the part D here. So as compared to the input image here, that it was a smooth portion, now we have a sharp image here. So fine details of the north pole of the moon can be better studied when we operate the input image with the help of the Laplacian filtered image, which is a sharpening spatial filtering. We have another example as well, where the use of these two masks over the input image can also be explained here. So the scanning the electron microscope image with the help of these spatial filterings here, the corresponding results you can see here, and as compared to the input visualization, we have good visualization with more details onto the resultant images here. Now under this category we have the applications as like the unsharp masking and that of the high boost filtering here. So the unsharp masking can be explained as a process used for many years in the publishing industry to sharpen the image, that consists of subtracting a blurred version of the image from the image itself, and this is nothing but the unsharp masking. So I hope blurred image is very well known to you people. Sharpening operation, I hope you have understood. The mathematical representation of this unsharp masking can be better represented with this mathematical expression here, and a generalized representation for the high boost filtering can be modified to this particular form here. So HB into the small casing is to represent the high boost filtering here. Now here we have the example filter mask of this particular type here. Now you can see that at the central pixel the intensity level is quite higher as compared to its neighbors here. That case are kept to the 0 values here, and rest of all are at the -1 here. So the central pixel intensity is having a definite change, a sharp change neighbor pixel values here, or the coefficient values here. Here it is a plus 8. So a is any constant value which is greater than or equal to 1 here. So these two masks when utilized, they will of course give us the use of unsharp masking and a high boosting into the spatial domain filtering here. The example is again for the same input image here, the scanning electron microscope image, the Laplacian for the input image having a is equal to 0, and when we put the value of a to be equal to 1 and further here 1.7, we see the good visualization with more information details into the image here. Also we can have just a note on the use of first derivatives for the enhancement, and this is into the case of gradient here. When we have the second order derivative, it is the Laplacian operator, and when we have the first order derivative, we know it by the name gradient here. So the gradient with respect to the input intensity of the pixel represented f as a function of x comma y. So x and y, of course the coordinates here can be operated with the gradient operation here. So this is what the gradient we show. So gx and gy are arranged into the columns. So this is the partial differentiation of the pixel intensity f with respect to x and y here. So the magnitude for such a gradient can also be computed by taking the root of the summation of the individual squares here. Now, next to that, we have the example filter mask to be used for the first order casing here. So we have this example mask here. The first mask having the representation of the coefficient values right from Z1, Z2, Z3 up to Z9 here. The description here it is for the 3 by 3 region of the image here, and now we can use it for the spatial filtering here. Now we have the visual effect better explained with the help of this example, where we have the optical image of the contact lens here, and here the defects onto the boundary of 4 and 5 o'clock can be better visualized when we find out a Sobel gradient here. So Sobel gradient, the age detection is basically by the use of the gradients here. So gradient is the first order differential operation onto the input intensity here. So it cannot be better judged into the input image here, but when we get the Sobel gradient here, so these two bends we can better judge. So we can have the quick judgment of whatever there it is not uniform in the image here. Now coming to what type of the questions can be there into your examination here. So with respect to the basic spatial filtering, the question can be as like, justify the statement median filter is an effective tool to minimize the salt and pepper noise through simple illustration here. So as we are provided such a question into our examination here, so we have to justify this statement that it is underlined here, and for this justification we have to make the use of simple illustration. So for this case we have to take input image sample on our own. We have to perform the median filtering over it. The input image should have first of all the salt and pepper noise into it, and we have to demonstrate that by performing the median filtering on such input image. There it is a minimization into the noise here. So let us start having this particular question solved here. So we consider the image corrupted by salt and pepper noise. So now what is salt and pepper noise here? So salt refers to the high gray level value, whereas pepper refers to the low gray level value here. Now the random occurrence of the white and black values is generally termed as the salt and pepper noise here. So the black and the white dot when you see into certain image, and those are totally unwanted, this is nothing but the original image corrupted by or the affected by the salt and pepper noise here. So such an example we can take that is represented into the matrix form like this here. Here we take the 3 rows and 6 columns here. Now these are the circled pixel intensities you can see into the 8-bit environment. 255 is the maximum brightness level we can opt for. It is a complete white. 0 is nothing but a complete dark here. So rest of all the pixels are having various values. They are having gradual changes with respect to one another, but these two are having sudden changes here. So this is nothing but the noise here. The loss of information has occurred here, and that we have recover by operating it with the help of the median filtering here. Now what is the first task here? We have to judge that the input image is having the two values 255 and 0. So these are different from its neighbors here. So 255 is equivalent to the salt noise and 0 is equivalent to the pepper noise. So this is the first of all the identification very necessary, and when we have a proper identification, then we have to select a proper median filtering mask here. So let us have the minimum possible dimension, that is of the order 3 by 3 here. When it is applied, so let us carry out it step by step here. We have the first step to apply it onto the value 255 here. You can see with the help of the dashed line the certain region has been overlapped by the mask here, and at the central position we have to coincide with the pixel under consideration, and that it is affected by the salt noise, hence showing the pixel intensity 255 here. Now this particular portion is not into the consideration. We have to discuss about this much of portion for the median determination here. Now whatever the 9 pixel intensities here we have to arrange them into the ascending order. So the lowest value is 21, then next to that we have 22, 23, 24 two times, then we have 32, 33, 34 and 255. Then we have to determine the median here. So median is the middle, so we can be striking out from the left hand as well as from the right hand side to get the exact median value here. So the output value is 24. We have to replace the value that is affected by the salt type of noise represented 255. We have to replace it with the new value as per the median filtering, that is. So this is non-linear type of the spatial filtering here. Now we move forward and we represent it in this particular form. Now we have again to arrange the ascending order as we have shifted the mask by one location here, and again determination of the median here, and this is for the value, new value is 25, the earlier value that it was 24 here. Next to that, when we go beyond, we have to apply it onto again the right hand side by shifting it, by sliding it here. So you can see here, as we talk about salt and pepper noise, 255 is the representation of the salt noise, and this is the pepper noise represented by the 0 pixel intensity here. Now this has to be replaced by determining a median here. So the median is to be determined out of these 9 values arranged into the ascending order, striking out from the left as well as the right hand side here. The middle value is your required thing here, that it was 28, and after substitution you can get the output image filtered by median filtering here. Lastly, we again slide this particular mask onto the right hand side here, and we get the 26 replaced by finding the median here. So you can see here the median value that it was 26, and after replacing all the values here, so you can see the 255 value that it is now 24, and the 0 value that it is now 28. Now the 24 value that it was here, into the subsequent step that it was to be replaced by 25 here, whereas the 26 lied the same here. So this is what the output image that is generated by processing the median filtering here. So the changes already I have discussed with you people. 255 replaced by 25, as well 0 is replaced by 28 here. Now here we have the observation that salt and pepper noise are the values replaced by a value similar to that of their neighbors here, and from this it is evident that the median filter is an effective tool to suppress the salt and pepper noise. So this way you can answer to the question. So the question was to justify the statement here. So the statement is justified, and for that purpose we have taken the help of the illustration here. So in this illustration, there it was the input image sample selected here, and 2 of the pixel intensities were representing salt noise and correspondingly the pepper noise, and we have successfully replaced them by the median filtering operation. So in the similar manner, based on to the spatial filtering, you can come across another question into your examination. Here we have the problem question statement starting from: filter the following image using a 3 by 3 neighborhood arranged by assuming first of all a 0 padding and secondly a pixel replication here. So this is what the question. Now we have to find out the answer here. So step by step we shall go for. Now the first case we can go for first of all the zero padding here. Now for zero padding here we can expect the mass of the dimension 3 by 3 for the averaging purpose here. Now here it is the step for zero padding. Now in the zero padding, if zero padding is to be assumed the image is padded with 0 along the edges, we represent like this. So whatever the dashed portion that it was represented, inside this dashed portion including this one is the intended image here. So this is what the input image, and as we have to deal this particular image sample by zero padding, so all the borders are added by one entries, of course, onto the top, onto the bottom, onto the left hand side and onto the right hand side. The dimensions are increased by adding 2 to that particular dimension here. So if the original size of the image sample that it was small n by n, so it will be n plus 2 by n plus 2 you can go for. Now in this particular case we have now added the zeros here. Now next step will be to perform the averaging here. So for averaging purpose, a mask of the dimension 3 by 3 we have to slide, and the first thing that it will be starting at the origin. So origin of the image sample under consideration is the top left corner pixel here. So here it is the image sample and here it is the top left corner portion 1 here. So when we don't have the zero padding, the mask will be like this here, and there it will be nothing at these places here. So it won't be a good thing to operate the mask like that. So because of this we pad the zeros, and the coefficients, those are logically designed with respect to the filter mask here, will have the pixels beneath them to coincide for with the zero values padded thereupon. And we can have the averaging here. We can find out the summation of all these ones divided by 9, that depends on the dimension of the neighborhood or the size of the filter mask here. Now by the next step, when we go further here, the summation to be replaced, the average to be replaced for the intended pixel location here can be determined like this. We have all this summation. So 0 added with 0, 0, 0, then 1, 2, 0, 4, 2 here. So the summation is going to give you 9 here. When it is divided by 9, you get it to the value 1 here. When the filter mask is of the dimension 4 by 4, so you have to make the summation of the 4 entries divided by 16 value here. So for the case as just now illustrated in the previous, so we have the average value calculated, that is equal to 1 here. So what it was 1 by this particular task, it is 1 again. Now we go on shifting it. So while shifting it to the right hand side, we get this illustration here. So now the center of the filter mask will coincide to the pixel value having represented by 2 here. Now when we determine the average of all the pixels into the neighborhood here, we have the average counted like this. So the computation will be 0 added with 0, then again 0, 1, 2, 3, 4 added by 2 and 5 here, and this summation is to be divided by the 9 here. So 3 by 3 is 9 here, and the obtained value will be 1.89. We have to round up this value to a nearest real number here, and 1.89 can be rounded to 2. So in this similar fashion, whatever the other pixels here we have, so the illustration we have shown for 1 as well as for 2 here, we have 3, 2, 4, 2, 5, 1, 1, 2, 6, 3, 2, 6, 4, 7. So for all of them we can make the computations here. So here we have for the pixel represented by 3 here, the computation of the average value after 0 padding gives us 1.6676, and it can be rounded to the value 2 here. Next to that, we have the computation of average for the pixel represented by 2 here. So the addition gets us to the value 11, that is to be divided by 9. So it comes 1.22. The nearest closest integer is not 2, it is 1 here. So we have to replace it by 1 here. So average value of the pixel represented by 4, the addition comes out to be 12 here, divided by 9, we get it to the value 1.33. Rounding up, it will be 1 here. Now the average value of the 2, we get it to the 26 by 9, so it is 2.88. And finally, rounding it to the next integer, it will be 3 here. The closest integer, it will be 3 here. The average value of the pixel that it was represented by 5, the addition is like 2 plus 3 plus 2 plus 2 plus 5 plus 1 plus 2 plus 6 plus 3. So this is equal to 26 divided by 9. The value comes to be 2.88. Rounding up it is equal to 3 here. Now for the pixel represented by 1 here, the addition comes out to be 20. When you divide it by 9, you get it 2.22. Rounding up to here, it is equal to 2 here. So here we have all these particular values. We continue for the other pixel values as well. We have the pixel represented by the intensity 1 here. The addition here comes out to be 17. When we divide it by 9, it is 1.88. The rounding up, it will result into the value 2 here. The average of the pixel represented by 2, the next to it is the 32 divided by 9. Here we have 3.55, rounded up to the value 4 here. The average value of the pixel represented by 6, the addition comes out to be 36 divided by 4. It comes exactly equal to 4. No need of rounding up the value here. Then we have the average value of the pixel represented by 3. So it comes 26 divided by 9. So is equal to 2.88, rounded to the value 3 here. So the average value of the pixel 2. So this is equal to 11 by 9, rounded to the value, it is equal to 1. For the pixel represented by 6 here, the value comes to 2.33, and rounding up gives out to be the answer 2 here. Then for pixel 4, we have it 28 divided by 9. The value is equal to 3.11 here, and rounding up to the value, it is equal to 3 here. Now for the pixel 7, the last pixel here, we have the addition of all the neighborhood intensities along with consideration of the zero paddings. It is equal to 22 divided by 9. So the value comes to be 2.22. Rounding it up, it will be equal to 2 here. Now whatever the original image that it was, by using a 3 by 3 neighborhood averaging filter mask here, so we get it to the new values as represented onto the right hand side here. So this is 3 by 3 average filtered image, the output image, by using the averaging filter of this much of dimension onto the original image. Here it is the output image here. Now we go for this second case here. So in the second case, again we are going to perform the averaging here, but this with respect to the pixel replication instead of the zero padding here. Now here into the pixel replication, as we are going here, we have to represent the pixel replicated one element outside the border by the same elements. Here we have 1 1 1 1 for the corner elements, 2 2 2 2, then 2 2 2 2, we have 7 7 7 7, and next to that we have the determination of the average value here. So here we can perform the average in the same manner as we have done it before. So here the procedure comes out to be with the value 2 for the pixel represented by pixel intensity 1 here. So in the similar fashion, we have for the pixel represented by 2, after shifting the mass to the right hand side here, the new value after rounding up is equal to 3 here. So in the similar way, we have the new values as like 2 2 2 3 3 3 3, 4 here. Next to that we have 4, 4, we have 3, 4, 5 and 5 here. So this way we have got a new output image after taking 3 by 1 of the filter mask here by replication of the pixel elements here. So this is what the output here. So I hope the basic spatial filtering is very much clear to you people. So we shall meet into the next live session where we can see the details of the filtering into the frequency